In this lecture, let's talk about array-based queue implementation, just like we did with Stack. There's many different collections out there. Arrays are the most fundamental ones. What is an array? Array is a fixed container that has a certain amount of elements inside. Some of the arrays, if they are not fixed, they can be resized. Nonetheless, when you start with an array, you have to basically specify the size of it. Otherwise, it would just be empty. Typically, when we're doing array base, you specify a default size capacity and say this is how much I want to allocate at runtime to implement my queue. But in this lecture, we're going to talk about bounded queue version and bounded queue lecture. But even before we get to this, I want to illustrate visually what this queue operation will look like from both enqueue and dequeue perspective using two pointers. Regardless whether you're using array-based or non-array-based collection to implement queues, you always have two pointers, right? One is the front of the queue and the other one is the back of the queue. This allows you to efficiently track the queue operations back and forth. For the purpose of discussions, let's use front and rear to mean the front of the queue and then back of the queue. And then we'll be using a capital letter to represent elements information. This means that by reference here, this queue has a fixed size, 5 elements inside. This is the array indexing, specifying each of these elements inside of this queue. As you can see here, the front of the queue is 8, sitting at index 0. Front and rear represent index, okay, not the elements inside of it. 0 specifies the index of the front, rear specifies the index of the rear. A, B, C, and D, these are elements. These elements information is tags. They say string A, B, C, and D. Okay, so with that in mind, let's move on to the next page. If you're using a fixed array, there are two ways you can keep track of the information. We're talking about queue here. When the information gets in, this information basically slotted to the very first elements. B comes after that, last in, first out. So A, B, C, D in that order, occupying index 0, 1, 2, and 3 respectively. Now, if you were to dequeue the front elements, dequeue means removes its reference. This used to have a reference to A, so that reference is basically a memory address. When you dequeue the front element, you nullify it. You make it null. So that element's gone. This is the empty now. In order not to waste space, the fixed front design that you would move every single element forward because you want to fill that spot. This allows you to keep track of your front. Fixed front basically means all of your front element is always going to be at index 0. Moving every element by one slot is O of n operation. So just imagine that you have 10,000 operations being requested on this queue. You know, every dequeue calls for O of n operations. This dequeue operation is very efficient. The challenge is making sure that you can keep track of your rear and also the front. And if you can do that, great. Making sure that front and rear do not cross each other. Obviously, if you keep track of the size of your queue, they should not cross each other. If they cross each other, that means there's only one element sitting in there, which is when A is first inserted, both rear and front will be the same. Otherwise, they should never cross. Knowing that fixed front design is a bad idea, let's move on to non-fixed front design, using what we call quote-unquote circular array. There's no such thing as circular array. Array is fixed, so you can't wrap the very last element inside the array to become the first of it. So what you need to do is to be really creative with your front and rear. This is what we call floating front design. Assuming this collection is fixed, it's got 5 elements in there. When you enqueue A, your front and rear are both 0, right? There's only one element, both front and rear are the same. When you enqueue B, obviously this moves your rear 1. When you enqueue another element, your rear increments by another 1. Step C, your front is 0 and rear is 2. So the very next operation calls for dequeuing. Dequeue is the same as before. From the fixed design, you just remove the reference to the very first one. And now your front is at 1 and 2. What we don't want to do is move those B and C forward to 0, because now we're doing the floating front. This front can change. I don't want to set it to 0 again. So what do? We don't care about moving everything forward. You just let the growth of your queue to happen. And so the growth of the stack is in this direction. You're going to run out of the queue's spot. You cannot enqueue any additional elements unless you throw that very last one to the first one. So you're tracking front is 1. Front equals 0. It's got to be empty by design, because we're using this approach. Nobody is occupying the very first element. Why don't we just push that additional element to the very beginning of the array and then set the rare be 0. So let's illustrate this. It's in the next slide. You're at the end, and then you have J and K, and then you want to do L. And L cannot be slotted index 5 because that's going to give you Q overflow exception. So what do? Because front is 3, you know there are 3 elements in front of your front, namely index 0, index 1, and 2. Naturally, your L will go into index 0. L specifies the end of your stack. It's got an index of 0, so your where is 0, but your front is still 3. In order for this floating front design to work, you'll be using modulus. Modulus gives you like what is the index here, and you want to do that fixed size, which is 5, to the effect of modulus 5. So whatever this n is, or this rare number is, that's the idea associated with the floating front. These are the 2 varieties that you see most likely with the floating front design for a fixed array implementation of Q.